Yes, if you have a question, you can ask.
Yes, sir. Sir, before you start the session, I just want to tell you that I was doing assignment one and two, and in that I have doubts in two questions. So, can you please resolve them?
Yes.
Should I tell the question number?
Uh, 1 second. Just wait.
Okay, okay.
Which assignment it is?
Assignment one and assignment two both. Question number eight in both of them.
Question number 8. Okay. Hmm. So, assignment 1, question number 8, uh, you have to calculate the specific heat, right?
Yes, yes,
So, uh, so question is calculate the ratio of specific heat gamma for uh, so gamma is basically Cp by Cv, right? That
yes.
is uh, 1 minus F, right? Something like that. Like degrees of freedom. Just a second.
I didn't use that formula. Wait, I can break it down.
Yeah,
Hold on a second.
it's like this. Yeah. So gamma is Cp by Cv into equal to 1 plus 2 by F. Okay, so F is the degrees of freedom. Okay. So here in the
Yes.
question, it mentioned it's an ideal diatomic gas. Okay. Uh, Ratios is a mixture of 1 mole of ideal diatomic and 1 mole of ideal triatomic. Okay. So what is the degrees of freedom for a diatomic gas? So diatomic gas, the degrees of freedom would be uh, if it's a rigid gas, then the its degrees of freedom will be 5, right?
Yes.
Hmm. And for triatomic gas, it would be uh, degrees of
I think that triatomic will also be 5 because it's linear, so it behaves like diatomic.
yeah, it should be six. No, triatomic gas is like it has three translational and yeah, so it depends upon how the like it's a linear or a non-linear. Okay, I guess if
Actually,
it's
it
a
is
linear,
triatomic
then
linear is given.
it's linear given, right? Yeah, it's linear. Yeah. So in that case, it would be five, I guess. One mole of an ideal diatomic and one mole of ideal triatomic gas. Yeah. So the gamma, in that case, gamma should be one, right? If you take the ratio. I mean, ratio of the like for diatomic gas, for gamma diatomic, it would be 1 plus 2 by 5, and for gamma triatomic, it should also be 1 plus 2 by 5. Right?
Yes, yes.
Yeah.
So it's coming 7 by 5. So, but 7 by 5 is here given as wrong answer. I also did the same.
For me also it is 7 by 5 came.
Calculate the ratio of specific gamma for a mixture of 1 mole of ideal diatomic and 1 mole of ideal triatomic gas. Hmm.
The statement,
Its answer is 7 by 4, 5 by 4. Accepted.
Yes.
Uh, something wrong, I guess. Then it should come 7 by 5. Yes. Yeah, it should come 7 by definitely. Like uh, diatomic, it should be 5 degrees of freedom. So 7 by 5. Maybe they have given wrong options. Like the accepted answer they have given wrong, I guess. Okay.
So, should I mail them about this?
You can mail them, I guess. I don't know the procedure, what to do, but you can mail them maybe. Okay.
Okay.
And second is week assignment 2, right? This is assignment 1.
Yes, assignment 2, question 8. Next doubt.
One, okay, one second, six. So it's saying that a molecule has just suffered a collision if the average distance it travels before it suffers two successive collision is the average distance it travels before it suffer two successive collision. Okay, so
I was thinking that since it is successive collisions, so it should be lambda, right? Because that is how lambda is defined.
it's kind of saying that first let's suppose um, it's like this, I guess. So the question is a bit unclear. So first let's take a molecule is moving. So it's first suffer a collision with one molecule. Okay, so this is the first collision. Okay, and after that it's saying it suffer another two successive collision. I think it's like that. So there
Yes.
are total three collision is happening, I guess. That's why the answer is there mentioned 2 lambda. If the success, if in the successive collision, if this contains the first collision, then if the answer would be lambda. Okay.
No, I was thinking since it is suffering three collisions, it should be three lambda.
No, no, no. It's saying that after the first collision, just suffered the first collision. Okay. So it already suffered the first collision. Okay. It's after suffering the first collision, the molecule moves like this. Okay. So then it suffer again a second collision. It moves lambda, and after having the second collision, it moves again lambda and suffer the third collision. So like this. So that's why it's coming to lambda, I guess.
Okay, understood.
Hmm. Okay. Okay. So yeah, if you have any doubt, you can ask. Okay.
Can I
So
ask something?
yeah, 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 you can ask.
Uh, Assignment 1, question number 9.
Assignment one, question number one. The mean kinetic energy of a molecule at 300 Kelvin is, and this calculate the approximate number of molecules per meter cube of an ideal gas of one.
Yeah. Actually, if I don't use this mean kinetic energy and all, if I use only this pressure equation,
Hmm.
P equals to small n kT, kBT.
P equals to small n kBT. Yes.
kBT.
Hmm.
If I use that formula, it is coming something different without using the first information. It extra parameter, yeah.
Okay. So L P equal to, so you have been asked to calculate the approximate number of molecule per meter cube of, 1 second. Yeah. So yeah. So here the in the question it's mentioned temperature is given. Okay. Calculate the approximate. So you are saying by using this formula you are getting some different answer, right?
There are two, extra parameter. Is it redundant?
Extra parameter means what is
Means
extra?
both we can use only single parameter, the pressure equation. Pressure.
Huh.
If I use this P equals to n kBT and we can find small n,
Hmm.
it is coming
It's
to one.
coming. You can also like both the ways you are getting different answer, right?
Yes, yes.
Hmm. I think it's better to use the kinetic because this pressure equation basically comes from some virial law. Okay, but the since uh, since the energies, the expression of energy is coming from this kinetic theory, so it's better to use the energy equation. Okay, but these factors are very important actually. Okay, so there are this correction and everything is there. Okay, so I guess it's better to use the energy equation in order to calculate this
Okay.
thing. Okay, because this
I think in real experimental setup, if in these conditions, the mean kinetic energy would not be 10 to the power minus 24 joules. It would be something else.
maybe. Mm, so it's saying the mean kinetic energy of a single molecule. Okay, so in general the pressure equation that we use, that is for an average kind of a thing. Okay, average pressure of the whole system. Okay, that gas equation pressure, that PV equal to NKT. This pressure is basically average quantity pressure, but here this not in general, the in the question it's mentioned the energy of a single molecule. Okay, that kinetic energy theory, from kinetic energy theory we are getting the kinetic energy of a single molecule. Okay, so in that way it's a bit different. Okay, so the definition of pressure here and there. Okay, so it's better to use that anyways.
Okay.
Yeah. Okay, so hmm. so so today's class of yesterday, like not yesterday, previous week we have mostly discussed about this mean free path. Okay, so we know like yeah, so we have discussed like when molecules gas molecule moves, so it suffers collision, and because of that it not moves in a straight way, it follows a zigzag kind of a path. And we calculated the mean free path, right? Mean free path, that is basically nothing, lambda is basically the average the average of the distance that is suffered by ETN number of molecules throughout the whole container, right? So similarly the collision time also we have calculated. Okay, that is similar concept, but now instead of distance it is the time. Okay, L by c bar, c bar is the mean speed, t into dn. And from that we basically got a very important equation, that is a survival equation, that is given by this. After n naught, initially if there is n naught number of molecules, after traveling a distance x, what is the survived number of molecules? Similarly nt is this n0 e to the power minus t by tau. Okay, after a certain time t. And then from there we got uh, several expression of the lambda. Okay, there's the most accepted one is the second order. After doing the second order correction, the expression of the lambda was simply this. So lambda is equal to 1 by root 2 n sigma. Okay, this is the expression of the lambda. And yes, so yeah, so from there we have also calculated uh, from the mean kinetic energy theory, the pressure. The pressure expression is given by 1 by mn c bar square. Okay, so these are like very important quantities that we have shown. Like we have also solved problem which basically involved these formulas to solve this problem. Okay, so now in today's class uh, it's mostly on the transport properties of gas or any fluid system that basically obeys the ideal gas law. Okay, so first is the concept of equilibrium. Okay, so there are basically three types of equilibrium is there. One is called thermal equilibrium. So thermal equilibrium means there are no temperature gradients exist in the system. Okay, so like if this is a gas molecule. Okay, so every molecule in the gas, like this is assembly of gas molecules, so every molecules of the gas have should have similar temperature. Okay, if some other molecules have higher temperature and some other molecules have lower temperature, so it basically creates a temperature gradient. Okay, so the basically temperature will flow the heat will flow from the high temperature to low temperature in order to make the system in equilibrium. Okay, so this is called thermal. So system always tries to attain a equilibrium state, so that's why the temperature will flow from higher to lower side. Okay, next is called the chemical equilibrium. So for chemical equilibrium, so the density, so if suppose in a room, if you spray a deodorant or something, so initially the gas molecules will be dense in that particular area, and after certain time you will see the gas molecule will spread out throughout the whole room. Okay, so the reason because is that the gas basically all the molecules of the gas basically want to spread out uniformly throughout the system. So in order to basically attain this chemical equilibrium. Okay, so this is one type of equilibrium the system wants to attain, and third type of equilibrium is called the mechanical equilibrium. So basically mechanical equilibrium is basically when, like, in a in a gas assembly, if the forces are not homogeneous, like into the throughout the system, like some parts have higher force, some part of have lower force, something like that. So this basically creates a unbalanced force into the system, so system tries to attain a balance into the system, and because of that the system achieves this mechanical equilibrium. Okay, so because of all these three types of equilibrium, so if you basically perturb this system from this equilibrium state, the system during the phenomena, like during the process by using which the system tries to attain this equilibrium, during that process this kind of transport phenomena can be seen. Okay, so there are several types of properties are there. Okay, so first is the case is that, let's assume that in equilibrium, whatever the gas or fluid, whatever it is, it should obey the Maxwell's velocity distribution. Okay, so this is a very important rule that this gas or fluid has to obey, and there are several transport property that I have discussed. So first transport property is the viscosity. Okay, uh, viscosity is like, let's suppose a gas or a fluid is there. So if suppose there are two layers of this fluid is there, so let's suppose one layer is having higher force compared to the below layer, so it's moving faster and this moving slower. Okay, so what happens that because of that there will be a friction that is developing between these two layers of gas, and because of that, because of this friction, the molecules, some molecules from this is, let's suppose V1, this is V2, this is layer 1, this is layer 2, so some molecules from V1 tries to jump into V2, and some from V2 to V1 in order to gain an equilibrium such that both the velocity of these two layers become equal. Okay, and so because of that, the friction, this viscosity arises into the system. Okay, so viscosity, the definition of the viscosity is basically uh, tangential force per unit area per unit time. Okay, and this force that is that basically working between these two gas layers, the expression of the force is given by this formula, F equal to minus eta dA into du dt. Okay, this du dz, yeah, du dz. This du dz is basically the gradient, like the velocity gradient that I'm talking about. Like two layers are moving with different velocity, right? So because of that, there should be a velocity gradient. So this gradient basically defined by du dz. Okay, and this eta is basically known as the coefficient of viscosity. Okay. Next is the thermal conductivity. Okay, the thermal conductivity, the origin of the thermal conductivity is the this thermal equilibrium. In order to gain the thermal equilibrium, the system shows this thermal conductivity. So what happens, let's suppose in a gas, in a fluid or gas system, there is a temperature gradient. Okay, so let's suppose some part has higher temperature and some part has lower temperature. Okay, so we know the temperature flows from higher to lower in order to make the temperature of the whole system as a uniform. Okay, so because of that, the heat will flow. So that heat, the like thermal energy or the heat that will flow per unit area, per unit area and per unit temperature gradient is basically given by this quantity, that is q equal to minus ka into dt by dz. Okay, this dt by dz, so all of this so this negative sign, like here also or here also, you can see this negative sign. In the case of friction, as we know, the friction always works in the opposite direction where the object trying to move, right? So that's why the negative sign comes here. Similarly here also, the heat flows from higher to lower state, right? So it basically moves opposite to the gradient, right? So because of that, this negative signs comes here also. Okay, so yeah, and this k is basically known as thermal conductivity. Okay, this is known as Fourier's law of heat transfer. Okay, this law is known as Fourier's law of heat transfer. Okay.
K is thermal conductivity or coefficient of thermal conductivity.
Oh, like yeah, so like coefficient of thermal conductivity. Yeah, something like that. Yeah, yeah, it's a kind of a coefficient. Okay, like for a particular type of material, this thing is fixed basically. Okay,
Okay.
eta is the viscosity here, coefficient of viscosity. Yeah, coefficient of viscosity. Okay, so and third is the third is the diffusion. Okay, so diffusion is basically, you all know diffusion. Okay, so uh, let's suppose a gas container. So the gas molecule, if this is a denser, if this region contains a dense number of molecule and this contains a less dense molecule, so basically from high dense area, the molecule will travel to this less dense area, right? So this is basically known as the diffusion. Okay, diffusion of the gas molecule. So this is nothing but the transport of the molecules or the gas, and this basically happens due to the due to get the chemical equilibrium. Okay, so if the system is not in chemical equilibrium, if some part has higher density compared to other parts, so in order to attain this chemical equilibrium, the system shows the diffusion process. Okay, so uh, so the expression, so the flux, the molecules, that is basically denotes by J, that moves, is basically the expression of J is basically given by this d into A into dn by dz. Okay. So here also it's negative sign because the gas molecule moves in the opposite to the gradient, and this is known as Fick's law of diffusion. Okay, Fick's law of diffusion, and then d is known as the diffusion coefficient. Okay. So these are the basically main three things. Okay, the main issue, the uh, main point from here is that when like during, if the system basically, if you perturb the system from whatever equilibrium, like if you perturb the system from, let's suppose in from mechanical equilibrium, so in order to attain that mechanical equilibrium, the system will show this viscosity behavior. Similarly, if there is some temperature gradient and something arise into the system, so in order to basically attain the thermal equilibrium, the system shows this thermal conductivity. Okay, and third is if there is some inhomogeneity in the concentration of the gas molecules. In that case, so in order to attain this chemical equilibrium, the system shows this diffusion behavior. Okay, so these are the three types of transport phenomena that is basically shown by any like gas or fluid system in order to attain the equilibrium, these three types of different equilibrium. Okay, so next is we will basically get like this expression of this different types of coefficient, that is one is the eta, next is the d, and eta, d, and k. Yeah, so this expression of this three coefficient, that is the eta, d, and k, are very important. So how to get that expression? So in order to get that expression, you have to first calculate uh, you have to basically calculate like this like for different cases, what is the expression of this is inhomogeneous force or temperature gradient. Okay, for different in equilibrium, like out of equilibrium systems. Okay, and from that you have to calculate this expression. Okay, so there is a like let's take, so there is a general treatment of that. Okay, so let's consider a gas system. So let's take three layers of the system. Okay, one, two, three, and so these are the three layers, one, two, three. So let's consider any type of physical. There are basically three physical quantities here, right? One is the concentration, another is the temperature, and third is the basically what is this? Third is the basically force or the velocity of the system. Okay, so or the momentum. Sorry, force or velocity or the momentum of the system. Okay, so let's suppose any of the physical quantity. Let's suppose h. So second number has a reference physical quantity, that is h. The first layer has some physical quantity h that is a bit higher from the reference one, del h plus del z. So this coordinate I'm denoting as z, this as y, this as x. And third layer has physical quantity reduce h minus l by dh dz. Okay, so so in order to calculate calculate the flux, like in order to attain the equilibrium, like both of these two layer has to become the quantity, physical quantity in both the one and layer 1 and layer 3 should attain the same value which the reference layer is having, right? That is the h. So in order to do that, basically the molecules basically moves from this layer to this layer and this layer to this layer in order to get that equilibrium value, that is h. So so the molecule or the flux that is moving from layer number 1 to 2 or layer number 3 to 2, that we have to calculate, right? Now before calculating that thing, what we need to know is what is the value of L. Okay, so L is basically the separating distance between these two layers. Okay, now so the approximation of the assumption they have considered here is that so in between this adjacent layer the molecule should not suffer any collision. Okay, so L should be like this, that the molecule from uh, like molecule from adjacent layers, the moving from adjacent layers, molecule moving from adjacent layers should not suffer any collision. Okay, this is the approximation or assumption we should consider. Okay, so one have calculated the expression of the lambda. So most general expression of the lambda we can take is sorry, most general expression of L we can take as lambda, that is the mean free path. Okay, now if you calculated it for average by taking the average of the molecule, okay, in that case, so this is basically known as the zeroth order. Okay, this is the most basic case. Now if you consider the the complexity into the system, like by considering the average, what is the average number of molecules that will flow from one layer to another layer without suffer a collision, in that case if you do the average and all, in that case the expression will come as L equal to 2 3 by lambda. Okay, so this is the second order correction. Okay, yeah, so now
This is first order correction, right?
yeah, so yeah, this is first order, second order. So this anyway, so yeah, so this may be the first order. Okay, one second, let me check.
I actually had a doubt here that I was thinking that is second order correction possible in this scenario?
Just a second. Okay, so this one is, I guess they are doing, yeah, so second order correction can be done maybe. So like, yeah, so first order correction, second order correction is it done in the standard textbook?
No, no, no. I
Okay,
am thinking like in research, can it be done?
maybe it can be done. Okay, maybe it involves lot of complex mathematics. Okay, but maybe it can be done, I don't know actually. So
Okay.
here it's consider the velocity as fixed. Okay, the direction is only changing. Yeah. Okay, anyway, so here it's considered up to the first order. Okay, the expression of lambda, this L, that is the distance between the each adjacent layers. Okay, so anyway, uh, so throughout our discussion we will be using this first order correction only. Okay, so uh, okay, now so if you consider L as 2 3 by lambda, so next what you can do, you can basically calculate the flux. Okay, that the part that the molecule that moves from one layer to another layer. So that flux is basically given by this quantity, right? 1 by 4 in C bar into the particular quantity H plus 2 3 by dH dz. Okay, so this is basically the flux that is moving downward. Okay, like the particles that is moving downward, phi downward, and phi upward is 1 by 4 n C bar into H minus 2 3 by dz. Okay, now from this you can calculate the net flux. Okay, net flux, that is minus 1 by 4 m c by lambda dh dz. Okay, so this is kind of a general expression. Okay, so now h can be any quantity. Okay, so for the case of where like there is a velocity gradient happens into the system. Okay, like for the case of viscosity, like we have discussed, so for the case of viscosity there is a velocity gradient, right? So one layer moves with uh, this, let's consider as y direction, this is z direction. So one layer moves with a higher velocity vy plus delta v, and one layer moves, let's suppose, just with vy. In that case the gradient del vy is basically dvy dz into delta z, right? So yeah, so in that case the physical quantity, that is h, for this expression is basically the velocity, the momentum, that is the mvy, and dh dz is basically m dvy into dz. So basically you have to substitute this thing here. So after doing that we will be getting the net flux, the phi, as sorry, this is 1 by 3. Yeah, okay. Okay, so this phi net we will be getting if you substitute h and del h del z for the case of when the physical quantity is momentum. So in that case the phi net you will be getting as 1 by third m n c bar lambda into dvy into dz. Okay, now so if you basically compare this thing with the viscous force law, that is F equal to minus eta dA du dz. If you compare these two equations, you will be getting the expression of eta as 1 by 3 m n c bar lambda, or you can write it like this also, 1 by 3 in terms of rho, depending upon the problem. Okay, if in the problem it's mentioned rho, the density of the gas, then you have to use the rho. If it's mentioned the number density, then you have to use this formula mn c bar lambda. So rho c bar lambda. Okay, yeah, and lambda expression you already know, lambda is 1 by root 2 n sigma. So yeah, so if you just substitute here, and sigma, we know sigma is basically pi d square. So if you substitute these two quantities here, okay, it's not here, here we will be getting the expression of eta as m c bar into root 3 by 2 pi d square. Okay, yeah, so nn will cancel. Okay, so yeah, so as you can see, so eta is basically, so c bar we know, so this is a very important expression to remember actually. Okay, yeah, this is also important, I mean depend upon the problem. Okay, so here you can show, so eta is basically dependent upon, so c bar is as dependent upon the, like proportionally dependent upon the square root of the temperature. So that means eta also dependent upon the proportion to square root of the temperature. Okay, yeah, and so if you calculate the dimension of the eta, so eta dimension should have the dimension of force divided by the dimension of area and dimension of the gradient. Okay, velocity gradient, that is du by dz. See, if you check all of these, if you like substitute the dimension of the force, the area, and the velocity gradient. Uh, so the force we know ml uh, square, it's L square and it's secant inverse. Yeah. So if you calculate it, so the expression would be m L inverse secant inverse. Okay. So that means in CGS unit, the eta has unit that is known as poise, and in SI unit, the eta has unit of kg meter inverse second inverse. Okay, and one poise is basically equal to 0.1 kg meter inverse second inverse. Okay, so this thing I think you have to remember, because in the problem maybe whatever unit it has been mentioned, so you have to use according to that. Okay, so you have to maybe convert the unit from CGS to SI or SI to CGS, something like that. So for this you have to remember. Yeah. Yeah, so similarly the next thing is the so here we have discussed about the gradient of momentum or force that causes the velocity difference between two layers. So in that case we have taken the quantity, the physical quantity, as the momentum. Okay. Next thing is the we can take the physical quantity as the temperature. Okay, not the temperature, that is the heat. Okay, so yeah. So if you take, so let's suppose there are two layers, similar way, two layers, both having different, one having hot and one is, let's suppose, cold. So that means the molecule will transfer between each other, right? So to get a equilibrium temperature between, like hotter hotter to cold, cold to hot, something like that. So the basically during this process the system basically wants to attain a equilibrium temperature, right? So let's, in this case, our quantity would be the heat, that is Q, that's basically getting transferred, right? So Q is basically CMV, this is a specific heat per molecule into T, and dQ dz is CMV into dt dz, and the flux is basically phi is 1 by 3 n c bar lambda CMV dt dz, right? Okay, now if you similar way here we know, right? So previously we have compared it with the Newton's viscous force law. Now for this case we will be comparing it with, what is this called, Fourier's heat law, right? That is Q is minus K dA dt by dz. Now if you can compare this, so the expression of the K, that is the coefficient of thermal conductivity, the K expression is given by 1 by 3 and lambda c bar c vm. So here c bar is the velocity, and here this other c is basically mean velocity, other c is the specific heat. Okay, heat capacity. Yeah, so yeah, so here also hmm. So here also you can write it in different form, right? You can write 1 by 3 as c bar into CVV, where CVV basically is the heat capacity per unit volume. Previously it was heat capacity for a single molecule. Okay, now here you can basically n is basically number of molecules by volume, so you can multiply this thing with CMV. uh, so n into CMV gives you CVV, that is the heat capacity per unit volume. Okay, per unit volume. Also you can write it like this also, 1 by 3 lambda c bar into rho by m Cv. Okay, where Cv is the molar specific heat at constant volume. Okay, so Cv is basically Na into Cvm, which is the molar specific heat. Okay, so here also you can write so here also you can write k bar equal to 1 by 3 lambda expression. You can substitute here also 1 by root 2 what is the in in sigma n lambda n c bar into cvm. So here n will cancel, so you'll be getting 1 by root 2 3 root 2 into pi d square c bar into cvm. So here also you can see the this kappa, this is not k actually, this is called kappa. Okay, so this is basically proportional to c bar, so that means here also is proportional to the t, since c bar we know 8 by pi kbt by m. Okay, yeah. Yeah, so similarly we can calculate the units of k also, or kappa also. So kappa is like its units is given by joule second inverse meter inverse Kelvin in, means I definitely. Okay, or you can be written as joule per second is known as watt, right? So you can write it as watt into meter inverse or Kelvin inverse. Okay, now there is also a relation between, so this is a very so this is one expression to remember, and this is one expression to remember. Okay, and there is a relation between eta and kappa. Okay, so eta expression is written by this 1 by 3 mn c bar lambda, kappa is 1 by 3 n c bar lambda c vm. So you can write kappa by eta as cvm by na into m into na, so it will give you cv by m. So this basically gives you kappa into m into eta into cv equal to 1. So this is a relation between both the two coefficient. One coefficient with related with conductivity, and one coefficient is related with eta viscosity, that is eta. So yeah. Next is the, so we have calculated the viscous coefficients for the case of thermal equilibrium and mechanical equilibrium, and lastly for chemical equilibrium, right? So so the chemical equilibrium, it's the density, so because of the density gradient the molecule will move, right, in order to attain the chemical equilibrium. So here the layers would looks like this. So here this is the layers. Okay, so one having denser, one is lighter. So one has basically high numbers of molecules, the density of the molecules are high basically here. Here the density is low. So the density, so this basically creates a density gradient, right? So here the physical quantity is given by the density of the molecule n, and here dH dz basically dN dz. So that means the flux that will move is minus 1 by 3 c bar lambda dN dz. Okay, yeah. So now similarly, if you compared with the Fick's law that we have discussed, that is basically the flux of the molecules that moves from denser to lighter region, that flux expression is basically given by the Fick's law. So d into dA, this is the expression of the Fick's law, dn dz, right? So if you compare these two equation, the expression of d basically given by 1 by 3 c bar lambda, right? Now here, so c bar, so now here you can write 1 by 3 8 by pi kbt by m, and lambda you can write 1 by root 2 n 1 by 2 n sigma, right? Yeah, sorry, n sigma. Yeah, n sigma. Now here you can write, so here you can see n you can write as uh, so uh, p equal to n kt, right? So you can write n as p by kt. So d you can write as 1 by 3. If you substitute here the expression of d, so you'll be getting root under 8 by pi kb by m. So t, so there is t square root of t is there, so if it will multiply with another t, so it will give t to the power 3 by 2. There is a root 2 here, and p is also there in the denominator, and sigma is pi d square. Okay, so that means here the diffusion coefficient d is related to the 3 by 2 power of t, and it's inversely proportional to the pressure. Okay, so unlike the previous cases where the coefficient of viscosity is not basically dependent, the thermal coefficient of thermal conductivity is only dependent upon the square root of temperature and independent of pressure. Similarly, the eta, the coefficient of viscosity, also there is only dependent on the square root of temperature. But here the diffusion is both dependent upon the pressure, the inverse of the pressure, and the temperature with the exponent 3 by 2. Okay, so here also you can also write relation between eta and d. Okay, like the viscosity coefficient eta, that is given by 1 by 3 mn c bar lambda, or you can write it like this also, 1 by 3 rho c bar lambda, and d we know is 1 by 3 c bar lambda. So uh, so if you take the ratio of both d and eta, it will gives you 1 by rho, right? So that means d rho by eta is equal to 1. So this is also constant basically. Okay, so basically relation between the diffusion coefficient and coefficient of viscosity. Okay, the next thing is the molecular effusion. Okay, so molecular effusion is just if suppose in a container, if there is a very small, if you make a very small hole into the container, okay, so this will, so since there is a gas molecule inside the system, right? So because of the pressure, this gas molecule so the gas molecule will tries to flow from this small hole, right? Yeah, so so because of that there would be some flux that is moving out from this small hole, right? But now before writing the expression of the flux and all, so in order to this molecular effusion to happen, there are three assumption you have to take. Okay, this small hole, this mass size, the diameter of the small hole should be much more smaller than the effective, if this is the diameter of the hole, this diameter should be much more smaller than the mean free path of the gas molecules. Okay, this is one assumption. Second assumption should be so molecule leak out without any pushback. So basically the molecules which are closer to this this hole, that molecule only should leave, okay, because since the hole is very small, okay, so it's not like a very, if it's a very bigger hole, then many molecules at a stage can move out, but it's not like that. So the molecule leak should happen without any pushback, okay. And because of that, there is, like, we can ignore the pressure density that will be developed between this hole, since the molecule will comes out at a very small rate, right? So since because of that the pressure gradient would be very small, so we can basically neglect the pressure gradient. We should consider that there is no pressure gradient or density gradient that is happening in the vicinity of the hole, okay. So no pressure or density gradient, okay. Yeah. So if we consider all of these three things, then only we can qualify this phenomena as a molecular effusion, okay.
In normal diffusion, is there pushback?
Hmm.
In a normal diffusion case, is there a pushback?
Normal diffusion case.
Yes, yes, because you are saying in effusion no pushback. So in diffusion, is there pushback?
Yeah, yeah. In effusion there is pushback. Yeah. No, sorry. In diffusion there is pushback. Okay.
Yes.
Hmm. Okay. So yeah. So that means the number of molecules. Okay. So if let's suppose the flux is phi. Okay. 1 by 3 n c bar. Okay. In that case, the number of molecules that is moving out per unit in a area of A in unit time dt is given by dn equal to minus phi into a into dt, and dn dt is basically given by minus phi into a, okay. And if you calculate the, so now you can also calculate in terms of molecular mass also, so dm dt would be m into phi a, and volume also, it's since decreasing, so you can write this expression in terms of volume also, so dv dt equal to minus phi a into n. So phi is basically given by 1 by 4 n c bar. Yeah, you can write like you also know the expression of n, that is p by k n k kbt, and c bar. Okay, 8 by kbt by m. So you can substitute the expression of n and c bar here. So by doing that, you can also get the expression of phi like this: 1 by 4 p by kVt into 8 kVt by pi m. This gives you phi equal to P into Na into root 2 pi mRt. Okay, so this is the expression of phi. Okay, yeah. So now
dvdt is minus phi a by n or minus phi a by m?
dv dt phi
Yes,
by
yes.
m.
I was thinking that by dividing the dndt expression with n, we get dvdt, right? So it should be by n, I think.
Okay, n is basically the number density. Okay,
Yes, yes, yes.
uh, so from m. Okay, we'll check it. Okay, I'll check this thing. What it should be
Okay.
more n. Okay. Anyway, so now we will go to the problem section. Okay. The first problem is determine the mean free path of air at STP given that viscosity eta is 1.7 in 10 to the minus 5 Newton dot second per meter square. Mean velocity c bar as 4.5 into 10 to the power 2 meter per second, and density rho as 1.29 kg per meter cube. So in that case we have to calculate the mean free path. Okay, so yeah, so the options are option A 0.88 into 10 to the power minus 5 meter, option B is 0.58 into 10 to the power minus 7 meters, option C is 8.78 into 10 to the power minus 8 meter, and option D is 2.9 into 10 to the power minus 8 meter. Okay, yeah, so we know that the expression of eta is basically 1 by 3 c bar rho lambda. Okay, so here lambda is basically given by 3 into eta into c bar by rho. Okay, so here in the problem everything is mentioned. Okay, so the value of eta, that is 1.7 in 10 to the power 5 Newton per second by meter square, it's mentioned. C bar is mentioned 4.5 in 10 to the power 2 meter per second. Rho is mentioned as 1.29 kg per meter cube. Okay, so these three quantities are mentioned. Okay, so now, so thus substitute all this thing here. So just by substituting it, so all the values are substituted here. So after doing the substitution, you'll be getting the lambda as 8.78 into 10 to the power minus 8 meter. Okay, this is a straightforward problem. Now the problem 2, calculate the diameter of nitrogen molecules from the following data. So first data is coefficient of viscosity is given. Is given by 7.3 into 10 to the power minus 6 Newton dot second dot meter square. The density of gas is mentioned 1.25 kg per meter cube. The number density is also mentioned, that is 2.7 into 10 to the power 24 meter cube. So these three quantities are mentioned. So from there you have to calculate the diameter of the nitrogen gas. So options are given. Option A is 9.5 into 10 to the power minus 10 meter. Option B is 2.1 into 10 to the power minus 10 meter. Option C is 7.4 into 10 to the power minus 10 meter, and option D is 4.2 into 10 to the power minus 10 meter. These are the four options are given. Okay, so how to solve this? So basically similar way, so eta is given by 1 by 3 n c bar rho, right? Sorry,
Rho c bar lambda.
rho c bar lambda, yeah, rho c bar lambda. So here the lambda is basically given by 3 into eta by c bar into rho. So from here lambda we can calculate, so 3 into, so eta is given 17.3 into 10 to the power minus 6, c bar is given 450, and rho is given 1.25. So if you calculate all of this, you will be getting 9.2 into 10 to the power minus 8 meter. Okay, now so lambda we know, lambda is basically 1 by root 2 n sigma, right? So sigma is 1 by root 2 n pi d square. So we have been asked to calculate the diameter. So here d is basically the diameter, so d is basically 1 by root 2 of root square root of root 2 n pi lambda. If you just substitute this thing, all this thing here, you'll be getting 1 by square root of root 2 pi into 2.7 into 10 to the power 24. That is the number density is given, into 9.2 into 10 to the power minus 8. Okay, now if you calculate all of this thing, you'll be getting d as 9.5 into 10 to the power minus 10 meter. Okay, so this is the way. So basically so it's all basically game of substitution and all, using the formula and doing the proper substitution. Okay, so basically eta, rho and n is given. So Eta expression is related to rho c bar lambda. So lambda is basically 3 eta by c bar rho. So from there you get the expression of lambda, that is the mean free path, and mean free path is related to the diameter of the gas molecule. So by using that rule, lambda equal to 1 by root 2 n sigma, sigma is pi d square. So from there you can use this formula to get the expression, to get the value of d. Okay. Question number 3 is calculate the diameter of oxygen molecule at STP if its coefficient of thermal conductivity is given by K equal to 24 into 10 to the power minus 3 joule into meter inverse into second inverse Kelvin inverse, and CV equal to 20.9 joule per mole inverse, no, kilomole inverse into Kelvin inverse, and the mass of the oxygen molecule is 5.31 into 10 to the power minus 26 kg. Okay, so in that case, what is the diameter of the oxygen molecule? Okay, the options are given. Option A is 1.0 into 10 to the power minus 19 meter. Option B is 1.2 into 10 to the power minus 9 meter. Option C is 1.6 into 10 to the power minus, sorry, this is 9. Option D is 2.1 into 10 to the power minus 9 meter. Okay, these are
The
the
mass is given as 10 to the power.
hmm?
What is the mass of O2 molecule? I can't read the 10 to the power.
5.1 10 to the power minus 26. Okay, let
Okay,
me
okay.
write it properly. Minus 26 kg. Okay. Yeah. So to solve the question, first you have to calculate the C bar, that is the average speed. So okay, yeah. So first what we need is the expression of the K, thermal conductivity K. That requires many things. As you can see, 1 by 3 density C bar lambda and the heat capacity CV, that is already mentioned. Okay. So we have to substitute all of this thing. Okay. So let me first write. So it's STP, it's mentioned. So pressure and all is 180. So K, the expression is K is basically given by 1 by 3 m n c bar lambda cv. Okay.
M is not given. M is not there, I think.
No, no, M is given.
Mass of
Mass of
oxygen
water
molecule
molecule.
given.
But expression M is not there.
Let me check.
Oh, yes, yes, yeah.
It's thermal conductivity kappa, right? Oh. Yeah. So, 1 second. Here you required because in the expression, okay, this specific heat, okay. So in the original expression, it was 1 by 3 m 1 by 3 n c bar lambda cvm. Okay. Now cv, that is the specific heat, is basically related to m into cvm. Okay, so because of that you need the mass of the oxygen molecule. Okay, sorry, yeah, cv, I am written it in a wrong opposite way. cvm equal to m into cv. Yeah, so 1 by 3. So now here, so you have to calculate all of these things. So c bar is given by root under 8 kt by pi m. Lambda is given by 1 by root 2 pi n sigma square. Now if you substitute all of this thing here, we're getting kappa as 1 by 3 into root 2 into cv by pi sigma square into m into root under 8 kbt m root under 8 by pi m kbt. Okay, so mm will cancel. Sorry, this square root of m will be still there. So this should be here 1 by square root m. So it will be like this. Yeah, it will be like this. Yeah, so this is the expression of the kappa. Now from here you have to calculate the sigma. So sigma is basically, sigma square is basically 1 by 3 root 2. If you substitute the quantities here, 20.9. So cv's expression is given 20.9 into 10 to the power 3. The m expression is given, that is everything, this whole thing can write under root under. So 8 into 1.38 into 10 to the power minus 23 into 5.31 into 10 to the power minus 26 into 273. Since it's in STP, so we are writing the temperature as 273. So yeah, okay, so this thing is divided by pi. So after doing all of that, the sigma we will be getting as 1.2 into 10 to the power minus 9 meter. Okay, yeah. The next is question number 4. The coefficient of self diffusion of oxygen at 273 Kelvin and 1 atm pressure is given by 1.8 into 10 to the power minus 5 meter square second. Estimate mean free path. Okay, so the option A is 1.27 into 10 to the power minus 7 meter. Option B is 3.8 into 10 to the power 7 minus 7, sorry, 10 to the power minus 7 meter. Option C is 0.8 into 10 to the power minus 7 meter, and option D is 0.4 into 10 to the power minus 7 meter. Okay, so these are the given options. So okay, so the diffusion coefficient, we know diffusion coefficient is related by basically this quantity 1 by 3 lambda c bar, right, where c bar is basically root under 8 kt by pi m. Okay, now for this problem, you have to calculate the expression of the diffusion, right? So first you need to calculate the expression of c bar. Okay, so for c bar, uh, uh, so k is given, t you know, t is 273 Kelvin, and mass is basically, mass means here the mass of each oxygen molecule, right? So we know that 32 gram of 32 gram of, that is 1 mole of oxygen contains na numbers of molecules, right? So one molecule should have mass of 32 gram by na. Now since here in the problem everything is mentioned in SI and all, okay, yeah, so it's better to
We
use.
can write 8RT by pi capital M.
Hmm?
Automatically, 8RT by pi capital M. M is the molar mass.
Yes, I am
Yes,
also solving that way.
That will be
that
easy.
way also you can also write, okay, molar mass. But yeah, in that case you have to use RT. Okay,
SI unit we can use.
yeah, that way also you can do. There are many ways. Okay, here this way is like it's just converting the mass. Yeah, that way also you can do.
Okay, okay.
Yeah, 6 Na. The substitute this thing here. Uh, expression of M is this. This is basically M. This is basically T. Kb you already know, and lambda. So you have to calculate the lambda thing. Okay, lambda is basically 3d by c bar. So 3d is the diffusion. Okay, sorry, yeah, 3 is the diffusion coefficient, self diffusion, that is given by 1.8 into 10 to the power minus 5. An expression of c bar is easily can be calculated from here, like 8 into pi into, sorry, 8 into kbt, right, 8 into 1.38 into 10 to the power minus 23 into 273 divided by pi into this thing m. If you do the calculation, We'll be getting the expression of lambda as 1.27 into 10 to the power minus 7 meter. Okay. Yeah. So question number 5 is a closed vessel is partially filled with liquid mercury. Okay. There is a hole of area hole of area 10 to the power minus 7 meter square above. Okay. The above the liquid level. Okay. Above the liquid level. Okay. The vessel placed in a region of fatal temperature after 30 days it's found to be okay. Estimated. Okay, so the vessel is placed in a region of high vacuum at 273 Kelvin. Okay, so the vessel is placed in a high vacuum region. So that means the outside of that vessel, it's there is no air basically. Pressure is very low. High vacuum at 273 Kelvin, and after 30 days after 30 days the vessel basically weight is lower by the amount uh, found found to be lighter by 2.4 into 10 to the power minus 5 kg. Yeah. So estimate the vapor pressure of mercury at, so estimate the vapor pressure of mercury at 273 Kelvin. Okay, yeah. So the answer is, so in equilibrium, so this is basically the effusion. Okay, so this, in order to solve this problem, you need to the concept of effusion, because you know, see, this hole, the size of this hole is very small, pretty much small. Okay, 10 to the power minus 7 meter square, the area of the hole. So it's 10 to the power minus 7. Okay, so that means the size of the hole is very small. So the molecule will effuse from here. Okay. We know that since it's a effusion problem, so we have to use what in the question it has been asked to calculate the vapor pressure. Okay, estimate the vapor pressure. Okay, yeah. So for that we have to use the formula for effusion. Okay, so the formula for effusion is this is the effusion, the flux. This is the flux of the effusion, right? This formula. So you have to use this formula here. Okay, so here phi we know P into 2 pi m kVt. Okay, hmm. Yes. So now from here what you can do, you can write, since the area is mentioned, so you can write, you can multiply the area both sides because area is needed. Okay, so phi is mentioned, rate of change of mass. Okay, so in order to calculate the rate of change of mass is basically, job mass is basically, that means that that thing that uh, dm by dt, right? dm by dt. Okay, so the that rate of change of, in order to calculate the rate of change of mass is basically mass into phi into a. Okay, phi is the flux into the area. Okay, because area is needed. What is the so if you multiply phi, mass of the particle in, multiplied phi into a, so this basically gives you the dm into dt. Okay, so now from here we can calculate, so p into a into root under 2 pi m kVt. Okay, so now from here if you multiply, we first multiply a with both the sides, now we multiply m with both the sides, m into p into a into root under 2 pi m kVt. Now from here, if you calculate, now if you calculate the whole quantity, so if you multiply here dm by dt, that is basically would be equal to p into a into root under m by 2 pi kVt. Okay, Now from here pressure would be equal to root under, so pressure will come this side, so this thing will be multiplied to the left hand side, so 2 pi kbt into n into 1 by area into dm by dt. Okay, yeah, so now just substitute the thing. Okay, so p, okay, so one thing is mentioned here, okay, that I forgot to mention, the molecular mass of mercury. Okay, the molecular mass of mercury is 200.59 atomic mass unit. Okay, u. So p is basically this. So now just substitute 2 into pi into 1.38 into 10 to the power minus 23 into 273 divided by 200 into 59 into 1.66 into 10 to the power minus 27, okay, into 1 by area. Area is 10 to the power minus 7, right? dm dt, that means the change of mass by day. So 30 days if the change of mass is 2.4 into 10 to the power minus 5, right? So it should be into 2.4 into 10 to the power minus 5 into by 30 into 24. Since it's everything is second, okay, right, so it's better to convert everything in seconds. Okay, 13 to 24 into 3600. Okay, because we generally calculate rate and all those things by second inverse, like joule second inverse or something like that. So it's better to convert the units into the seconds. Okay, so if you calculate all of this thing, you will be getting the expression as 0.0247 Pascal. Okay, so this is a problem of effusion. Okay, so the thing is like, yeah, so this is the formula, right? This formula you have to remember actually. What is the yeah, this one. Yeah, so this thing you have to remember, dm equal to minus m phi a. So that thing I've substituted here, right? And after that dm dt is given, so dm dt expression substituted here, like here. So from that we get the expression. Okay, yeah. The next problem is thermal conductivity of a gas assembly at temperature T is Kelvin at a given density of n. What will be the fractional change in thermal conductivity if the number density is increased 3 times? So the options are 25%, option B is 50%, option C is 100%, and option D is none of above. Sorry. So yeah, so thermal conductivity we know K is okay. So K expression is basically given by half 1 by 3 into m n c bar lambda cv, right? Or you can write it like this also, 1 by 3 n c bar lambda cvm, okay, whatever the way you want. Okay, now from here if you substitute lambda equal to 1 by root under root n sigma here, and n as sorry, c as c bar as root under 8 kBT by pi m here, then you will be getting, so if you do that, the n will cancel, right? This n and n thing will cancel, so K is just be some function of square root of temperature, right? So in that case the K is basically doesn't, the thermal conductivity coefficient, so not K, it's kappa basically. So kappa is basically independent of any gas density n, right? So if you increase the gas density, nothing will happen to the system, okay? 3 times, 4 times, 5 times, nothing will happen. So the correct option would be option D, okay? Since you can see number density will cancel, I mean, or like initially there is expression of n there, but if you substitute the lambda expression here, so n will cancel. So after that the K is just become a function of one variable, that is root T. So since it's not dependent on the n, so changing the n doesn't give basically any effect onto the heat capacity, okay? Sorry, thermal conductivity. Yeah. So question number 7 is calculate the diffusion coefficient D of H2 gas at 300 Kelvin and 1 atm pressure, given the mean free path lambda is 17.91 into 10 to the power minus 8 meter, okay? So the options are, option 1 is, option A is 2.12 into 10 to the power minus 4 meter square second, option B is 1.06 into 10 to the power minus 4 meter square per second, option C is 3.18 into 10 to the power minus 4 meter square per second, and option D is 0.53 into 10 to the power minus 4 meter square per second, okay? Now, so basically in the problem, sorry, lambda is given, that is 17.91 into 10 to the power minus 8 meter. Temperature is given, that is 300 Kelvin, okay? So now so from that, using those two things, so you need to calculate the d, right? So d is basically 1 by 3 lambda into c bar, right? So so you need the c bar. Okay, so c bar you can calculate easily since you know the temperature. 8 kBT by m. Okay, now just you have to just substitute it here. Okay, 1 by 3 into 17.91 10 to the power minus 8 into c bar, whatever the value is. The mass of hydrogen atom also you know. Okay, so after doing that, the value of d will be getting as 1.06 into 10 to the power minus 4 meter square per second. Okay, 7, question number 8. An astronaut goes for a spacewalk and her spacesuit is pressurized to 1 atm. Okay, uniformly a tiny piece of space dust punctuates her suit and it develops a small hole. Okay, of radius 1 micrometer. So that is very small, right? 1 micrometer, 10 to the power minus 6 meter. Okay, around. So it's very small. So it's you get, right, when in a pressurized gas chamber. Here it's astronaut suit of astronaut. So here since there is a very small hole that is developed, so it's a problem of molecular diffusion, right? So what is the force? So force is simple, right? So uh, what is the force? Basically force of the diffusion gas. Okay, force of the diffusing gas. So it's just simple. So options are 9 into 10 to the power minus 7 newton. Option B is 5 into 10 to the power minus 6 newton. Option C is 3 into 10 to the power minus 5 newton. Option D is 3 into 10 to the power minus 7 newton. Okay, now so uh, okay, so the force is, pressure into area, right? So this is as simple. So just pressure, that is 1 atm. So 1 atm you have to convert into newton per meter square, right? So that is around 1.013 into 10 to the power 5. And it's a small hole, so you can use the area of a circle. So pi into r square, so 10 to the power minus 6 whole square. So this will give you, if you calculate it, it will give you 3.18 into 10 to the power minus 7 newton. This is the expression of the force. Okay. Yeah. Okay. Now the question number 9. So this is a very easy problem. So next is question number 9. Consider a container divided by a partition with a small hole of diameter d containing the same gas on each side. So same gas in each side. So a container that is separated by a partition, and that partition is small hole, and each of the, so the container basically contains same gas, so each of the partition of the container also have the same gas, okay, in each side. So the gas on the left hand side is temperature T1. So the gas in LHS has temperature, so has temperature T1 and pressure P1, okay. And in RHS, right hand side has temperature T2 and pressure P2, okay. Now if the D is much smaller than lambda, so that means D is much smaller than lambda, that means you already identify that problem as a molecular effusion problem, okay. The equilibrium is achieved achieved by the flux balance. In that case, what is the condition of the equilibrium? Okay, so first is pressure should be equal to the pressure 1 should be equal to pressure 2. Option B is temperature 1 should be equal to temperature 2. Option C is P1 by T should be equal to P2 by T2, P1 by T1. Option D is P1 by root under T1 should be equal to P2 by root under T2, okay. So these are the options are given, okay. Now now from here, since it's mentioned that these two are the in the container, so flux on coming from 1 to 2 side and flux that is coming from 2 to 1 side, so phi 1 2 should be equal to phi 2 1, right, in order to attain the equilibrium, okay. So this is a small hole of radius d, small hole. So you have to use the rule of the formula of the flux for the molecular effusion, right? So that means phi expression you already know, that is r n by c bar, and since in the problem everything is mentioned in terms of pressure and temperature, right? So you have to write all of these quantities in terms of pressure and temperature. So n is basically k p by kBt, and c bar is 8 by kBt by lambda, right? So just substitute it here, so it will give you 1 by 4 into P by kt into 8 kt by pi m. So it will be proportional to P by root T, right? So from 1 to 2, phi 1 to 2, it should be equal to P1 by root T1, and phi 2 to 1, it should be proportional to P2 by root T2. Okay. So for the equilibrium, P1 by root T1 would be equal to P2 by root T2. So the final answer would be this one, option D. Okay. So you understand, right? So you have to use the concept of flux. So this is our last problem. Okay. So if you have any question, you can ask. Otherwise, I will stop the slides. Okay.
No question, sir. Thank you so much.
Yeah. Okay. So thank you for your attention. Okay. So I'm just ending the slide.